Hi everyone, this is our last lesson, well our last theory lesson on stoichiometry for now. Then we're going to look at a prac, and then we're going to be moving back to physics, so we'll be looking at forces. So the last thing we're looking at in stoichiometry for now is reacting quantities, which is using what we've learnt so far, but looking at a whole reaction, a whole equation. So if we look at this equation here, we've got magnesium and hydrochloric acid reacting to form hydrogen gas and magnesium chloride. And what we're interested in is the coefficients. So we need twice as much hydrochloric acid as the amount of magnesium we have for this reaction to occur. So what this means is that for every one magnesium atom, we need 2 acid particles. So, I mean, there's a hidden one there. So for every 1 magnesium, we need 2 hydrochloric acid particles, and that's going to react to give 1 molecule of hydrogen gas and 1 formula unit of magnesium chloride. So similarly, as it says here, if I have 100 magnesium atoms, I need 200 acid particles to react. Let's have a look at the first example. Okay, so we want to calculate the mass of sodium that must react with sufficient water to produce 7.95 grams of hydrogen gas. So I know that if I have 2 atoms of sodium, I'm going to get, if I have enough water, just 1 molecule of hydrogen. Okay, hydrogen gas. So I can compare the amounts, which means I can compare the number of moles. If I have 2 moles of sodium metal, then I'm going to get 1 mole of hydrogen gas. I can't compare based on the masses because they weigh different amounts. I can only compare based on the numbers. So I know how much hydrogen gas I want to produce here, and the question is how much sodium do I need? So I need to compare the numbers, or the number of moles. So the first thing then that I need to do is I need to convert this mass of hydrogen gas into how many moles of hydrogen gas it is. So the number of moles of hydrogen gas is the mass divided by the molar mass. So the mass of hydrogen gas is 7.95. The molar mass of hydrogen is 1.008, and in a molecule I have 2 of those. So 2 lots of 1.008 is the molar mass, and that gives me 3.94 moles of hydrogen gas. So I need twice as much sodium to produce that. So I'm going to write that down. You don't need to write a sentence based on that. I'm just writing a sentence because this is the first one we're doing. So we would need 2 sodium atoms. 2 sodium atoms are required. How do you spell required? Not like that. With 1 hydrogen gas molecule. Okay, so if I have 3.94 moles of hydrogen gas, I need twice as many moles of sodium. So the number of moles of sodium required is 2 lots of the number of moles of hydrogen. So that's 2 times 3.94, which is 7.89 moles. Okay, now I know the number of moles, so how much sodium I need, but the question is calculate the mass of sodium. So the mass of sodium, if I just rearrange this formula, is the number of moles of sodium times by the molar mass. And the number of moles we just found was 7.89. And the number of moles, the molar mass of sodium is 22.99. Now, these coefficients outside the front of the element or molecule or whatever is just to compare amounts that you need in the reaction. You'd never use the number out the front when you're considering the molar mass. So here where I've got the molar mass of sodium, it's just one sodium, okay? I don't double it because of that too. I've already taken that into account here, okay? Any little numbers though you do have to consider in the molar mass, because one hydrogen molecule, for example, does have two hydrogens in it, so the molar mass is 2 lots of 1.008. Okay. Anyway, if I put that in the calculator, I get 181 grams of sodium required to produce 7.95 grams of hydrogen gas. Okay, let's do the next example. Barbecue gas cylinders contain propane gas, so that's C3H8. When the gas is burnt, the products are water vapor and carbon dioxide. Balance the chemical equation representing the reaction. Okay, so I'm going to leave oxygen till last because it appears on its own there, so that should be the easiest one to balance. So I can do either carbon or hydrogen first. So if I go with carbon, I've got 3 carbons on the left-hand side. So for there to be 3 on the right-hand side, I need to triple the amount of carbon dioxide. Then I'm going to balance the hydrogens. So on the left-hand side I have 8 hydrogens. On the right-hand side I have 2. So I need 4 lots of that so that I have 8 on the right-hand side as well. Now I'm going to balance the oxygens. So on the right-hand side I have 3 lots of 2 is 6 plus 4 is 10. And here I have 2. So I'm going to need 5 of those to make sure I have 10 on the left-hand side as well. Now, the barbecue cylinder contains 4.5 kilograms of propane gas. Whenever we do chemistry, we use mass in grams. So always convert to grams when we're doing chemistry. This might get a little bit confusing because when we do physics, you'll find that we always have the mass in kilograms. So you need to remember chemistry has the mass in grams and physics has the mass in kilograms. Okay, so I'm going to need to convert to grams. So the mass of propane, which is C3H8, is 4,500 grams. Okay, so what mass of oxygen is required for complete combustion of the propane? Now, again, I can't just compare the masses, I need to compare the amounts. So to do that, I need to be using the number of moles. So the first thing I'm going to do is find the number of moles of propane gas. So the number of moles is going to be the mass divided by the molar mass. So I'm going to need the molar mass. So I'm going to find that first. So the molar mass of propane is 3 lots of the molar mass of carbon, which is 12.01, plus 8 lots of the molar mass of hydrogen, which is 1.008. And that comes out to be 44.09 grams per mole. Now that I've got the mass and the molar mass, I can find the number of moles. So remember, your communication here is super important. Always say what you're finding the number of moles of. Okay, so don't just do N equals M over M. It's the number of moles of propane gas. So is the mass divided by the molar mass. So we've got 4,500 grams divided by 44.09 grams per mole for the molar mass. So that comes out to be 102 moles. Okay. Now, I want to know the mass of oxygen. To find out the mass of oxygen, I first need to know the number of moles of oxygen, because the mass is the number of moles times the molar mass. So the number of moles is required to find that. So what is the number of moles of oxygen? Well, how many oxygens do I need for each propane? For one propane, I need 5 oxygens for this reaction to take place. So I need 5 times as much oxygen. So the number of moles of oxygen is 5 times the number of moles of propane gas. So that's 5 times 102. And that gives me 510 moles of oxygen. But of course I need the mass. So the mass of oxygen is the number of moles times the molar mass, which is 510 times the molar mass of oxygen. And again, I've already taken the 5 into account. I only use that when I'm comparing between number of moles for the ratio of oxygen to propane. It's not included in the molar mass. The molar mass of an oxygen molecule is what we're interested in, not the molar mass of 5 oxygen molecules. So the molar mass of an oxygen atom is 16, but we have 2 in an oxygen molecule, so times by 2, and 510 times by 32 gives me 16,330 grams of oxygen. Okay, that's part A. Now we're doing part B, the mass of carbon dioxide produced by combustion of propane. So I already found that the number of moles of propane in 4.5 kilograms is 102 moles. So now I can find the number of moles of carbon dioxide that's going to be produced, because it's going to be 3 times as much. So the number of moles of carbon dioxide is 3 times the number of moles of propane, which is 3 lots of 102, which is 306 moles. Now, the mass of carbon dioxide is the last thing here, and that is the number of moles times by the molar mass. So the number of moles is 306. The molar mass of carbon dioxide is going to be 1 carbon plus 2 oxygens, and that gives me 13,476 grams of oxygen. And that's the last example in your book. I'm actually going to do one more example because I just want to show you how it's a bit different when the one you're starting with has a different coefficient. So for example, if this question had have had like a 2 there or something like that. So I have created this question, so you might like to copy this down somewhere. So I've got barium hydroxide and aluminium sulfate reacting to form barium sulfate and aluminium hydroxide. So that's a double displacement reaction, which it doesn't matter if you don't know what that is. Okay, so 24.3 grams of barium hydroxide is reacted with excess aluminium sulfate. How much aluminium hydroxide will be produced? And I've got the molar masses here so that we don't have to spend time calculating those. Okay, so I know how much barium hydroxide I've got, the mass, but I need to find the number of moles, otherwise I can't compare between barium hydroxide and aluminium hydroxide. So the number of moles of barium hydroxide is the mass divided by the molar mass, and the mass is 24.3 grams, and the molar mass is 171.3 grams per mole. So that gives me 0.142 moles. Now, the number of moles of aluminium hydroxide is what we're interested in, so we've got that so far. The number of moles of aluminium hydroxide. So the ratio is a little bit different here. I can't just times by 2, because for every 3 barium hydroxides that I react, I get 2 aluminium hydroxides. So the ratio is a little bit different. So the way that we do it is we times by the one that we're finding out how much there is. So I want to know the number of moles of aluminium hydroxide. So I times by the 2 that's at the front of aluminium hydroxide, and I divide by the one we already know. So I'm coming from barium hydroxide, so I'm going to divide by 3. Okay, which makes sense because for every 3 barium hydroxides we need 2 aluminium hydroxides, so for every 1 barium hydroxide we get 2/3 of the amount of aluminium hydroxide. So I need to times by 2/3 of the number of moles of barium hydroxide. And people find this really confusing. People find this whole lesson really confusing usually, so please don't stress if you're feeling a little bit lost. It just takes practice. Okay, so 2/3 of 0.142 is 0.0946 moles. So therefore the mass of aluminium hydroxide is the number of moles times the molar mass of aluminium hydroxide, so 0.0946 times by 78.0, which is given up here. So I get 7.38 grams produced. And that's the end of that. So the questions to do are on page 34 and 35, and it's under reacting quantities. You should have already done the ones above that. So there's only 6 questions, so question 1 through 6, and then underneath that it's got general revision problems. So you might like to do those now, or you might like to save those until we've sort of given you a test date for this topic. But yeah, do those reacting quantities one. So in other matters, the physics test will be the first week back, and we will have a stoichiometry assignment, which we might hand out to you maybe the first lesson back. I might upload it now just so that if you want to, you can have a look at it before you come back, but it'll probably be due, I'd say, at the start of the second week that you're back. And then we're going to have a stoichiometry test about a week after that. So you will have a couple of tests coming up. Please let your teacher know if it's all getting a bit much. Okay, cool. Thanks very much.